Hello everybody, welcome back to my YouTube channel. In the last video, we covered what transformers are and specifically we looked at its encoder part when we were covering its architecture. Now we want to move to the decoder part and want to understand that what the decoder part is doing. But in order to understand that, there are two important mysteries that we need to solve. The first one is that in our multi-head attention block, there is an additional term here, masked. What masked multi-head attention is? The first mystery is this, and the second one is that in our second block, which is of multi-head attention, in that we don't have a single arrow here, right? We have additional arrows coming from our encoder part, because as we understood in our previous video, that in our encoder part, whatever output you get, if it's not the last encoder, then that output goes as input in the next encoder. But if it's the last encoder, then that output goes inside our decoder block. So this output is going as input in our multi-head attention block, which we call cross attention. So we need to understand these two terms. And once this is done, I think most of the things are already similar to our encoder block. So architecture wise, it will not be a big problem, but we will see intuitively that what exactly happens here. But for this video, the focus will be on these two things. And in the next video, we will cover what the entire architecture is in detail, covering the intuition that what exactly each part is doing and how they are interacting with each other and finally giving out the output that we need. And once that will be done, we will cover that how the inference happens in transformers. Okay, so let's move to this part now. So let's just first understand that what masked multi-head attention is. And before that, I want to highlight one thing here, that let's just know what multi-head attention is, right? When you have multiple self-attention blocks. So for now, to make things simple, let's just consider that I have a single self-attention block. Okay, now inside my self-attention block, what happens? That whatever word embedding I provide, let's say here I'm just considering one word for simplicity. Let's say I consider cat and I'm providing its word embedding that contains three elements. Now, whatever word embedding I'm providing, let's say I have a sentence, cat, mouse. What do I get out of my self-attention block? I get contextual embeddings, right? We covered everything in detail in our self-attention video. If you haven't watched it, I would highly recommend to please go and watch that video. So what do we get as output? Contextual embeddings, right? Now these contextual embeddings, how do we define them? Let's say I have cat. So contextual embedding of cat will be some weight, which we calculate through our self-attention. Then word embedding of, let me represent it by EW, word embedding of cat plus, let's say this is weight 1, weight 2, word embedding of taste plus some weight, which we calculate through self-attention, which we are, for this word embedding, we are saying it's with the word embedding of mouse, right? So what we are saying, that cat is actually made up of word embeddings of each of the words that are present in our sentence, right? Because this is what contextual embeddings are. They are, so word embeddings are basically, they capture the semantic meaning of the word. But when you calculate or when you find the contextual embeddings, that represents how contextually aware your word is. For example, if I say river bank and money bank, then the bank will have the same word embedding. But since they are used in different context, actually their embedding should be different. And that concept is captured by our contextual embeddings, and that is where self-attention comes in. We covered everything in detail in that video. So I'm not repeating now, but just to give you an idea of what masked multi-head attention is. So basically, from your self-attention block, whatever embeddings you get, those embeddings are dependent on your word embeddings of each of the word that came in the sentence, right? Now, what we are doing in the decoder part, that whatever understanding our encoder block has passed from the input sentences that we have feed in here, right? Whatever understanding our encoder has got, it is passing that information in our decoder block, right? So whatever is happening here, what we are basically doing, that we are producing output, right? And at the time of inference, what happens, that we get output one word at a time, right? The output is one word at a time. So let's say I provided a sentence here where we are doing next word prediction. So I wrote, this is an. Okay, this was my input. Now, what will happen here? That I will get apple from here at first time step, right? Then this apple will again go here, and then entire processing will happen. This is an apple off. Then again will happen. This off will go as input again. This entire sentence will go. So basically, what we are doing, that we are predicting one word at a time, right? It's not like you have provided the input sentence or whatever input phrase you had and you got the entire sentence at once. This is not things happen, right? Even in chat GPT, that whatever question you type, the output that you get, that is generated word by word. Basically, it's next word prediction, right? So output that you get is actually word by word. So the point that I'm trying to make here, that here what you are doing, that you are telling your model that this is my complete sentence. Okay, this is my complete sentence, and you are finding out the contextual embedding with respect to each of the word embeddings of the word that are there in the sentences. But at the time of inference, you will not have the complete sentence, right? So what you are doing, that it's not like you have a complete sentence, this is an apple, and then you're just passing this part. This is not how inference happens, right? What you are doing, whatever you are predicting at that time, you will not have the entire sentence. Otherwise, there would be no point of having a model if you already know everything, right? So when we are predicting, when we are testing, what we are saying, that our model will not have the information ahead of the time step, right? That is why this thing will fail, because if we are at chased, right? If we know, if we have reached to this point, we will not have the information that what will come next. We will not know that the next word is mouse. So that is why the contextual embedding of the cat should be dependent on the word embedding of mouse as well. We don't have this information. That is why we need to incorporate something in our model so that we are not letting our model cheat. Okay. Since at the time of inference, we will not have the entire sentence. That is why at the time of training, we don't want to tell our model that this is the entire sentence. This is the main idea. And how do we implement it? What do we do, that we know what self-attention formula is, right? We have our query metrics, we have our key metrics, we do their dot product, right? And it should be transpose. And then what we do, actually there is one scaling vector as well. We covered the details of it in the video. Then we apply softmax on it, and then whatever you get, you take its dot product with the value vector, and what you get is the contextual embedding, right? This is what self-attention is. Perfect. Now, how do we implement this? That what we want is that these weights should be zero, right? Because of these weights will be zero, then we will not be exposing the information. So what I'm saying, that let's say I'm finding out the contextual embedding of the cat, then at that time, I only my weight 1 should be not equal to 0. And other weights that I have, EW cat, EW chase, W3, EW mouse. So what I'm saying, that when I'm finding out the contextual embedding of the cat, then with these weights, W2 and W3 should be 0, because this information we don't have model to know, right? We want to hide this information from our model. Similarly, when I am finding out the contextual embedding of chased, then at that time we know that cat has come up, chased has come up, but we don't know that next is mouse. We don't have model to know that. That is why what we want, that V3 should be 0, right? So how are we calculating the weights? The weights are being calculated through this part. And how can we make the weights 0 without changing anything in the process? Because we want to the best things, right? We want everything to be same. We want to obtain the contextual embeddings, but in the decoder part, the only thing that we want to do is that how we are testing and how we are training, those should be on the similar lines. So if we will not have the data at the time of predicting or testing, then similarly, we don't want to expose the words at the time of training. Okay, because that would be cheating. We don't want our model to cheat, right? We want to protect it from overfitting. That is why we do it. So how do we make it 0? We have this part, right? We can do something about it, because this is giving us weights. So how do we do it? We are getting this, right? Q dot product of query vector and key vector, right? And how can we do it? What we do, that we introduce another matrix which we call mask, okay, which we call mask. Now this mask is nothing but matrix of zeros and minus infinity, zeros and minus infinity, okay. And why it works? Because the softmax, what we do, that we add this matrix in this part, we add this matrix in this part. So the softmax, wherever 0 is coming, so when we are adding it with the corresponding element, then that element will come as it is, right? So the weight will come as it is. But when it's minus infinity, when we are adding it with something, it will be minus infinity again. And the softmax of minus infinity is actually 0. So that is why the final weight matrix that you will get, that will have zeros wherever you have minus infinity in the mask matrix. Okay, so generally it's like what should I say, diagonal part. Okay, you will have minus infinities at one place and zeros at one place. Okay, so just to summarize everything, what do we do? That we have our query vector, we have our query metrics, and we have our key metrics. We take their dot product, we take their, we scale them, we take their softmax, and this is how we get our weights, these weights W1, W2, and W3. Okay, now what we are saying, that instead of directly doing everything like this, what we do, that we take this matrix and we add it with a mask matrix, which we are calling mask. And this mask matrix is nothing but a matrix of zeros and minus infinity. So let's say I have W1, 1, W1, 2, W1, 3. Okay. And I want to make these two weights 0. How will I make it? This is how my matrix will look. Okay. This is how my matrix will look. Whatever weights I want to make 0, At that place, I will have minus infinity. Then what will happen when I will add them up? Then it will be W11 minus infinity. And when I will take it soft max, then this will remain as it is. But these two quantities, since softmax of minus infinity is 0, these weights will become 0. So I hope masked self-attention is clear. So masked because we are using a matrix which we call mask, which is nothing but a matrix of zeros and minus infinities. Okay, and this matrix is then added to our weight matrix, and then we find out the softmax. Okay, so this part is clear. And why do we do it? Because at the time of inference, we will not have the information of what word is coming next. So that is why in the contextual embedding, when we are calculating it, at that time, we can't use the word embeddings of those words that are being coming as output at at the time ahead, right? So that is why during training, since we have all the data, we want to create similarities between the processes of testing and training. And we want that our model should not be exposed that information that this is the word that is coming next, because that will be cheating. We are already telling our model that this is the next word, but at the time of testing, we will not have that information. So that will be a big problem, right? So that is why, to provide similar conditions to our model, and to make our model more intelligent and less prone to overfitting, we use masked self multi-head attention. I hope this first mystery is solved. What it is, why do we do it? This part is clear. Still, if you have any doubts, do let me know in the comment section and I will help you in the best possible manner. You can also reach out to me on LinkedIn or Instagram. I am also available there with the same ID code on Xays. Now let's move to the next part, that is what is cross attention and why do we need it? Okay, so to understand cross attention, let's just first understand that the output that we get from our decoder, what are the factors that it is dependent on? The first factor is that what decoder has generated up till now. What decoder has generated up till now. So let's say we are doing next word prediction. So this is what our decoder has generated up till now. So the next word will depend heavily on what has been generated up till now, right? Because that is when the sentence will make sense. So this part we already captured it through our masked self-attention, multi-head attention, where the contextual embedding of a word were depending on the word embedding, so whatever has been generated up till now, right? So that part has been incorporated. The second factor is that what inputs or information we are getting from encoder. We haven't used that information up till now, right? Because whatever understanding we are getting from our encoder part, that is to be incorporated, right? Because that information is important. Encoder has done all the hard work to understand what inputs it has got. Now that understanding has to be utilized by our decoder block in order to produce the output. And how we are utilizing that information, we are saying that our output, let's say An is my output. This output is depending on the input sequence, right? So if I am doing, let's say I'm doing translation. So if I say this is an apple, let's say I'm doing Hindi to English translation, right? So my input sentence is Hindi and the output that I'm getting is English. You don't need to understand Hindi. If you are not familiar with this language, you don't understand this, then not a problem. I'm just considering an example here. Let's say you have यह एक सेब है. So this is sentence in Hindi and what does it mean in English? This is an apple, right? So the point that I'm trying to make here is that this an, the embedding of an, right? that also depends on your input sentences, your input sentence, right? Because whatever translation is happening, that is dependent on your input sentence, right? This "and" is dependent on this, but not every word is important, right? Not every word is important, because for "and" as to get "and" as output, this word has the highest important, because this is what we are getting as this, because this is the actual translation of "and," right? Similarly, for apple, in order to get apple, this input sentence is important. Every word has some role, but same has the most important role. In fact, this is the exact translation of apple, right? This is the actual meaning of this is the actual meaning in English, right? So how do we make this dependent on our input sequence? We use the concept of self-attention, where we consider the embeddings of our input sentence and we associate weights with it. So these are my embeddings of my input sentence, input words, and I'm considering weights with it. Exactly what we were doing in self-attention, but here, instead of word embeddings of the same sentence, we are using word embeddings of our input sentence, because what we want to understand, that how related my output sequence is with my input sequence. How related my output is with the input sequence that I have. But not every word will play an equal role. That is why we are associating weights with it. And how do we calculate weights? We use the same concept of self-attention, where we have query, key, and value matrices. But here, the query matrix will be extracted from our output sequence, and our key and value matrices will be extracted from our input sequence. That is the only difference. Else, exact calculation that we do in our self-attention block, that exact calculation happens. The only thing is, in cross attention, we have two sequences rather than a single sequence. We have both input and output sequences. And the second thing is that our query key value matrices are not from the same sequence. Our query matrix is from our output sequence. The final output that we are getting, it belongs to that. And the key and value matrices are extracted from our input sequence. And what are we doing through cross attention? We are trying to find out that how much related my output is to my input sequence, right? And since every word will not have an equal importance, that is why we associate weights with it, right? So we are finding out the dependence of our output sequence, output, w- whatever output we have, we are seeing how much dependent our output is on our inputs. And that is how we encode this information through our cross attention. I hope this part was clear. Still, you have, if you have any doubts, then do let me know in the comment section. And also one more thing here, that our cross attention, if you remember from our encoder decoder video, after that we discussed what attention mechanism is, and in that video we covered Bandhana's and Luang's attention. So what we were saying at that point, that initially they were using context vector, but since it were predicting a particular word, it's not like every word is equally important, right? If somehow we can pass this information in our model that this is the most important word in predicting it, right? So this same thing we are doing here. But since we want everything to be parallel, use self-attention as a base, and on top of that, we try to mimic our Bandhanau's attention, right? Because this is what we were doing in attention mechanism, right? We were somehow passing on this information in our decoder, that to produce this output, this is the most important input. Same way, to get this output, these are our inputs, But since we are associating weights, we are telling our model that higher weight represents that this is the most important one in producing this output. So basically, we are doing the exact same thing, but we are using self attention as base because we want to make everything parallel. Because this is what transformer is all about, right? Making things parallel. We want parallelism to come in. So I hope things are clear and both mysteries are solved. If still any doubts are left, then you can reach out to me and I will try to help you in the best possible manner. In the next video, we will cover decoder part in detail, and once this is done,
We will then look at the entire architecture as a whole rather than individual components of encoder and decoder. We will see how inference happens at the time of testing, what happens inside our transformer architecture. So that will end the transformer part, and then we will move to some more interesting topics in deep learning and generative AI. So stay tuned and subscribe to my channel if you haven't subscribed yet. Thank you for watching this video. If you like the content, give this a thumbs up and do let me know in the comment section if you have any feedback or any thoughts. I would love to hear. So thank you so much. Bye bye.